Hello. Today I want to look at this question that was posted recently on Reddit. And so the meme goes, POV, you walk into an interview and they hit you with which number is bigger, 3.14 to the pi or pi to the 3.14. Okay, so spoiler alert, the answer is 3.14 to the pi is slightly bigger than pi to the 3.14. And this is the top rated answer, that which also provides an interesting observation which is what we're going to try to prove and discuss today, which is this observation that Euler's number E is kind of special in the sense that you have numbers greater than that, then this thing kind of is true, but then if you have less than that, then it has the opposite effect, right? And then this person sort of has a sketch of a proof in the 5 steps, and I tried to look at it, but maybe I'm not following very exactly, but it's not exactly rigorous, which is understandable because it's Reddit, and you just want to provide some general idea instead of a detailed proof. But so that's the purpose of this video. We are going to try to make sense of how we can think about the general case, right? So okay, so I've calculated using a calculator. 3.14 to the pi is about 36.404, which is indeed greater than pi to the 3.14, just about 36.396. Okay, but we want to prove the general case. So what is it in the first place that we even want to prove? And so it goes something like this. So we let x in R, we fix it to be some positive real number, right? And all the numbers in question are going to be positive, because essentially to make sense of things like the real exponential function and taking the natural log, So x, the question then really is like, if you have some other number y, and how does that relate? Is it greater than y to the x, or is it less than, or is it equal to? Right, so it's basically about this relationship between x to the y versus y to the x. In other words, when you flip the base and the exponent, what's going to happen? Which one is greater, right? And then the question is, what does E have to do with all of this? E, which is Euler's number, which is something like 2.71828. Okay, so let's think about this. I'm gonna just represent this problem using this notation, this kind of like arrow, which is basically a placeholder for one of these symbols, essentially, but placeholder for some inequality or equality. And the idea is that the logic is that we're going to sort of do a bunch of manipulations just using this placeholder, and then we'll see whether it flips direction or not. And the idea is, if at the end, we get something like some equivalent statement that we can make better sense of, and that hopefully preserves the direction of the inequality. And since we have a chain of logical equivalences, the idea then is that that everything was equivalent, right? So let's do that. So let's start with, we see exponents on both sides. So what we can try to do is take the natural log to sort of bring down the powers. And again, everything involved, y is some positive number as well. So then, okay, so this y natural log of x versus x log of y. Okay, and the direction of the inequality is the same, because natural log preserves inequalities. It's an increasing function. So if h is less than b, natural log of a is less than natural log of b. This is the natural log, right? Okay, and then what we can do is we can divide both sides by divide this by x, and then divide by y, and and it doesn't change the direction of the inequality, because all positive numbers, x and y, are just positive numbers. So then you see that really the question of comparing this sort of x to the y versus y to the x is the same thing as comparing we notice this thing at the bottom is just the function f of z equals the natural log of z over z, and we're comparing basically the value of this function at x versus the value at y, right? So we have now made a nice observation that studying the comparison between x to the y versus y to the x is the same thing as looking at the height, the graph of this function f, and looking at the height of x, the height of f at x versus the height of f at y, right? So let's think about this. So the derivative, we're going to look at the derivative because we're concerned basically about where it has a maximum, or where is the derivative positive, which will tell us where the function is increasing versus a negative derivative, which would show where the function is decreasing. So let's take a look at that. F prime of z is f prime times g. So f prime of z is going to be the numerator derivative 1 over z times z minus f prime g minus f times 1 all over z squared. And so that's just going to give us 1 minus the natural log of z over z squared, which is equal to 0. We're trying to find a critical point. It's equal to 0 exactly when the numerator is equal to 0, which is the same thing as saying natural log of z is equal to 1, which is equivalent to z being equal to e. So we see that this function basically has this critical point at e. And if you do just a little bit more analysis, that 1 minus natural log of z, well, it's going to have the derivative is going to be negative between 0 and e. So this is going to be like a maximum point here. And it's going to be negative, means, the derivative is going to be positive between 0 and e. So it's going to be increasing. And then derivative is negative after e. So it's going to be decreasing. Something like that, okay? And so we kind of see that e is this special point, and I think that's kind of what some of the question was getting at, is that e is this sort of turning point where numbers less than it behave a different way, because it's this function is increasing, and then numbers to the right of it behaves the opposite way, where it's decreasing. And if we plot the number, let's say 3.14, right? That was the x in the original problem. And we kind of look at pi, which is maybe slightly over here. And so we compare them. Remember, comparing the 3.14 to the pi versus pi to the 3.14 is the same thing as looking at the heights of these functions. The height of f at these points. So we see that the height is taller at 3.14, and that means that this is a greater than. So we can do similar comparisons between any two pair of numbers x and y. Okay. So anyways, that's the problem. And so I think that the original question was looking at more like local behavior. It was saying that if you had 3.14 to the some 3.14 plus dx, right? Like x plus dx. So it was saying x to the x plus dx, and we're asking how that relates to x plus dx over x, and sort of the special time when it's when the slope is 0 is basically at e, or some equivalent thing to that, right? And so the point was that, well, if you have not two numbers less than e, let's say you have a number, let's say, I don't know, 1.2 over here, and you want to compare it with something nearby, 1.223 or something. And you can see from this graph that now instead of 1.23 Now sort of the inequality is going to be flipped around, so it's going to be 1.2 to the 1.23 is less than, right, because the height is lower at 1.2, 1.23 to the 1.2. And anyways, I think this graph is nicer because it generalizes the whole thing in one picture. And we see that, if we think of 3.14, it doesn't just have to be 3.14 to the pi that's greater than pi to the 3.14. It can be, from this graph, we see that it can be 3.14 to the, maybe like 5 or something, or even to 100. And this would still, 3.14 to the 5 would still be greater than 5 to the 3.14. And same thing with 3.14 to the 100. And if we're comparing the two numbers, you just basically look at the function f of z equals natural log of z over z, which essentially compares the ratio, the relative growth of natural log versus the y equals x.